Hello everyone again. Uh, as I mentioned in our first video, we will be continuing on the mechanical properties of materials, and I will be giving the concepts of force, stress, deformation, and strain. And in this video, I will be just looking at force and stress, and the next video will be about deformation and strain. So, what's a force? Again, I will try to explain this on a problem that you face before you enter into this civil engineering at METU program. You took an exam, and in that exam, I'm sure you were able to solve this high school physics problem. So my aim is not to show how to solve this problem, but my aim is to rather explain what those terms are. So in this problem, we have this object that we are trying to lift, and we are basing on the frictional forces on these blocks, the weights of these forces, and of course the friction between them. Now, let's take this strut and let's look at the forces that are applied on that strut. From this bearing block, the concrete block, there will be some reaction forces, Cx and Cy, and there will be some reaction forces at point A, Ax and Ay. So these forces are, we will be calling as external forces, and we define them as the forces imposed on that strut, and we can calculate those using the equations of equilibrium that you will be seeing in CE 221 statics course. But if you were to look a tiny little, or if you were to take a tiny little material from that strut, you will be realizing that the strut is exposed to the external forces, and because of those external forces, there will be some internal resisting forces developed within that material which we use in making that strut. Now, in CE 221, you will be analyzing some what's called statically determined structures that are subjected to some external loads, and you will be using the equations of equilibrium to solve such problems. And one problem is a truss problem. I don't know if you are yet over here or not, but in a truss problem, basically you have this structure, and whenever you apply some external forces, as you can see over here, you will be asked how to calculate the internal forces in that trusses. And replacing these hinges and the roller support with the appropriate reaction forces, and using the equations of equilibrium, the summation of the forces in x direction being 0, and summation of the forces in y direction being 0, and the moment about a point, let's say at point A, will be 0. Using these equations of equilibrium, you will be able to calculate these reaction forces, and all these forces are termed as external forces. Now, how about the internal forces? The internal forces will be developed on that rod over here. If you were to take that rod over here, you will be seeing that that rod is subjected to a compressive force, whereas this rod over here is subjected to some internal forces. Now, again, in that course, you will be facing, or you will be seeing beam problems, like you will have a beam that is subjected to all sorts of loadings, moments, point loads, distributed loads, and etc. And again, using the equations of equilibrium, you will be solving the reaction forces, and you will be seeing the external forces. Now, how about the internal forces? Well, you cannot see the internal forces unless you cut through that beam. And if you were to cut through that beam, you will be seeing that to bring this body to equilibrium now, because it's a statically determined structure, to bring that body to equilibrium, you should be able to put some forces over here. And that could be like a shear force, that could be like a normal force, or that could be like a moment. And these are now called the internal forces that are developed within that beam. So if we were to repeat now, the external forces are the forces imposed on the material, and the internal forces are the internal resisting forces developed within the material. And the simple structural analysis that you see in CE 221 can be extended to any load-carrying structure, and the internal forces are then expressed in terms of stresses. Let me try to explain it now. Like a more general problem, now you have a body over here which is in static equilibrium. So we don't have any inertial effects, and we are subjecting this to some loads P1, P2, P3, P4, etc. And whenever you subject this material to these external forces, there will be some internal forces developed within the body, as we have seen in the truss problem as well as the beam problem. Now, for the original body, we know that the equations of equilibrium, and if we consider a point Q within this body, we can realize that some forces are acting on that point which is located in that body. But how do we see that? Well, to see that, in order for us to see that, we have to get an imaginary cut through this object at point Q. Let's say that we will start with a plane parallel to the YZ plane. So in this plane, so we will be cutting right at that Q. And whenever we do so, now we have part of that body, and since the original body was in equilibrium, we should be able to say that this part of the body should still be in equilibrium. And the equilibrium can only be satisfied through the normal and the shearing forces. Normal and the shearing forces that act on that cut section, which is perpendicular to the x-axis, because we cut through the YZ plane. The normal of this plane is parallel to the x-axis. Now, if we consider a small area, delta A, at point Q, then we can represent those normal and the shearing forces by delta F and delta V respectively. And the shearing force that acts parallel to this plane can have two, or we can divide this into two. One acting parallel to Y direction, one acting parallel to Z direction. And we can label them now delta Vy and delta Vz. So the normal force acts perpendicular to that cut section, which is parallel to x-axis, and the shear force delta Vy and delta Vz acts parallel to the cut section, or perpendicular to the x-axis. Now, for a force acting on an infinitely small area, now we call that not a force but stress. So this delta A now we consider to be an infinitely small, meaning we take the limit of that. Limit delta A goes to 0. Delta F divided by delta A will be terming as a normal stress sigma xx. And the shearing stress will, like the tau xy, we will be calculating the limit as delta A goes to 0, delta Vy divided by delta A, and we'll be calling that dVy over dA. Similarly, tau xz will be dVz over dA. If I were to explain the stress, I can say that stress is the load intensity of the force and can be expressed as the force divided by the area. Imagine this guy sitting or laying on just several nails. Of course, those nails will punch in through that guy. But if you have a lot of nails, because of our body being able to resist a small stress now, this guy can lay on that nails. Now, if we repeat the same procedure for the planes parallel to xy and xz, remember we did cut that section parallel to the yz direction, so we were just looking at this side of point Q. Now if we were to cut parallel to zx, so we get this side, and parallel to yx, you get this side. Now we can then represent those stress components in the form of a stress tensor, and we can show them as S, the stress tensor. And these stress components, the first one that we have calculated, sigma xx, tau xy, tau xz, can be located in the first row of that. And the second row corresponds to this phase, which is tau yx, sigma yy, and tau yz. And the third row corresponds to that phase. And over there we have tau zx, tau zy, and sigma zz. Note that I have used a sign convention or convention. I labeled the normal stresses as sigma and the shear stresses as tau. And as I mentioned earlier, sigma normal stress acts perpendicular to that cross section, and the shear stress acts parallel to that. And in this sign convention, now as a tensor, it does not have just the magnitude and the direction, but it has one extra parameter in that, and that shows the plane on which it's acting. So over here, the first subscript indicates the plane perpendicular or normal to the axis. So sigma xx, whenever I say sigma xx, tau xy, tau xz, I'm saying that it is acting, those stresses are acting on an x-plane. And what is an x-plane? Its normal is parallel to the x-axis. And the second subscript indicates the direction of the stress component. So sigma xx, the first subscript tells us that it's acting on x-plane. The second subscript tells me that it's acting, or its direction is parallel to x. Similarly, tau xy is acting on the x-plane, and its direction is along y direction, tau xy. Tau xz it's acting on the x-plane, and its direction is parallel to z direction. Or now these stress components, sigma yy, tau yx, tau yz, see, the first subscript tells us that it's acting on the y-plane. Why is it a y-plane? Well, it's normal. Normal is parallel to y direction. And the second subscript tells me that it is acting on the y-plane, on the y direction, on the y-plane, on the x direction, tau yx, on the y direction, along z direction, tau yz. So this is called a stress tensor. Types of stresses. Now let's look at this billboard. On this billboard, there will be several loads or corresponding to stresses. The first one is static load. The weight of that billboard will cause some stresses at the bottom, and those do not change. Whatever the weight of that billboard, it will cause those normal stresses or shear stresses, whatever. But because of some winds, that load may change, and we can call them dynamic loads, and it will have different magnitudes at different times, and they will cause dynamic stresses that change. Let's talk about some simple states of stress. We can have like uniaxial tension, uniaxial compression, biaxial tension, triaxial compression, or pure shear, meaning that on a body we may not have all the stress components at the same time. Like in uniaxial tension, we can have only one of these stress components. In uniaxial compression, we can have just one of these uniaxial, see, along one axis, but this time it's compression. Biaxial tension, we can have two normal stresses at the same time. Triaxial compression, all three normal stresses act at the same time. Or pure shear, we don't have any normal stresses, but we have just the shear stress. Let me explain them using some examples. Again, let's go back to our truss problem. And simple compression, you can easily say that this member CG is composed of a rod, so it has a diameter, it has a cross-sectional area. If I were to divide the force acting on that rod to the cross-sectional area, I will get a stress component, and that will be the only stress component that exists on that rod. So that rod is in simple compression. Let's take another rod, like this time FG. This is in simple tension, as you can see over here. So it's a rod, so it has a cross-sectional area. If I divide the force to that cross-sectional area, I will get the stress. And that stress is now in tension. And that is the only stress that exists on that rod. Simple compression, it exists on this rock. See, it is carrying this huge rock through this cross-section. So the weight of that divided by the cross-section will give us a simple compression, or a simple compression in this bridge. Another example of simple tension is often seen in cables, and this is an example from a ski lift, and in the ski lift you have a drive shaft. A motor is attached to this drive shaft, and it rotates this drive shaft, and as it rotates this big wheel, and in this big wheel we have a cable that turns and carries the passengers from one part to the other part of a mountain, let's say, so that they can ski downwards. Now in this cable, if you were to take this cable, it can only carry a tensile force, and If you were to divide that tensile force to the cross-sectional area, you will be calculating the stresses, and this is a uniaxial tensile stress. Another example is pure shear that is often observed in plates connected by a rivet. Over here you have two plates that are connected by a rivet, and over here you have three plates that are connected by a rivet. And in the first one, if you are pulling this from both ends from a shearing force Fs, and if you were to take that rod right over here out, as you can see, you are pulling one end to the left, one end to the right. Now the forces over here that are acting on this cross section is parallel to that surface. Again, for this plate, if you were to take the rivet out over here, you will see that this is a double shear force, whereas what I mean is that you are pulling this part by force Fs towards left, the bottom Fs towards left, and in the middle you are pulling this with two shearing forces because it's in equilibrium, remember. Now if you were to look at the shearing forces, or if you were to take an infinitesimal area from those points, you will be able to calculate a shear stress. And there are no normal stresses, as you can see, and that's why we call this pure shear. And how we calculate it is as the shearing force divided by the cross-sectional area of the rivet. Pure shear is also observed in that ski lift problem that we mentioned. On this drive shaft, which is being turned by a motor, as I said, if you were to take this towards here, it is subjected to what's called a torque. So these moments are a torsional moment. And because of that torsional moment on the surface of that drive shaft, if I were to take that to the left over here, there will be some shearing force that is generated on the surface of that drive shaft. And to calculate the shearing stress, you divide the force to the cross-sectional area, and note that it is tau equals m divided by a0 times r. You are not supposed to memorize or calculate these because you will be seeing them, you will be calculating them in the CE 224 strength of materials class. Now, another simple state of stress is biaxial tension. Whenever you pressurize this tank with some pressure on the chamber wall, there will be some stresses that are going to be generated, which is these tensile forces on two axes. That's why it's called biaxial. And it's the same thing on this trampoline where the kid is jumping. On this trampoline, there will be these two tensile stresses, which are also called membrane forces or membrane stresses. They are shown as greater than 0 to show you that both of them are acting in tension. The last simple state of stress that I will be showing is hydrostatic compression, and it can be shown on this fish underwater. If you were to take an infinitesimal volume element from that fish, as you can see over here, from all three sides the same the same compressional stresses are acting on that fish, and it is shown over here as less than 0, pointing out that this is in compression. This ends the force and stress part of our video. In our next video, we will be looking at deformation and strain.